is Jens Kober. He's an associate professor from the Delft University of Technology in the Netherlands. He has been working in reinforcement learning for a while as well. Well, particularly in robotics and interactive learning. So we are happy to have you here, Jens. So it's all yours.
Thanks a lot for the kind introduction and for the invitation. I think that actually very nicely connects to what Benji was talking about. So, I mean, in the beginning of the previous talk, it was really more about learning to interact with people, but then the part about using advice to actually help the robot learn, that's exactly what I'm going to be talking about. Yeah. So, I mean, in robotics, typically you'd say a robot should help us humans, so we don't have to do all the tasks we don't particularly enjoy doing. However, in quite many settings, actually also we humans need to help the robot. And what I'm going to talk about in particular is having humans help a robot to learn a new task as quickly as possible, which then in the long run means that the humans can really adapt the robot's behavior to their own needs and preferences and teach them new tasks so they can help, the robots can help us later on. So it's really not about having robots teach us humans, but about humans teaching a robot. So how should we teach a robot? If you take a look at how humans teach and learn, what you'll notice is that it's not really a one-off thing like you often see in robot learning. So it's not I provide an initial demonstration or some initial optimization criterion reward function, but rather what you quite often will see is some kind of continued interaction between the teacher and the student. So have some intermittent interactions, maybe provide an additional demonstration, provide some advice or some feedback. However, I think that's now slowly picking up, but still largely missing in robot learning. And I hope by the end of the talk, I can convince you that actually making use of interactions during the learning process has huge benefits in terms of speeding up the learning process, which enables robots to learn more complex tasks and which is hopefully also intuitive for the human teachers. Okay, so I'm going to talk about learning through interactions. I know that the workshop is about reinforcement learning, but I'm still going to spend a couple of minutes to first talk about learn interactively or learning in imitation learning, so learning with interactions in supervised learning. The general setup looks something like that, and it's going to look very much like a reinforcement learning loop we often see, but it's actually a bit more general than that. So we have our robot, the agent, which is interacting with an environment. So we have a state, and then the robot has a policy and decides which action to take. Now, what we have additionally is a teacher in the middle. The teacher, we assume, is able to observe both the state the robot is in and the environment is in, and also what action the robot took. And then he or she can actually jump in and provide the advice. Or in particular, what I'm going to talk about is our corrections. So rather than having to provide the perfect action that should have been taken, the teacher needs to say, okay, you should move more in that direction, or you should move a bit faster, which turns out is a lot easier in many cases for human teachers to provide. So how would that look like for imitation learning? Carlos, who is also in the audience as far as I've seen, came up with an algorithm called Coach. And he's my postdoc now. So the idea is that in this case, car is supposed to drive on the right of the road down the lane. And initially it has this red policy. And then whenever the teacher feels like it and feels that the robot is doing particularly badly, he or she can provide interactively corrections while the robot is moving. So push it inside. And then you do that for a couple of iterations, and hopefully in the end, you have to do less and less interactive corrections, and the robot can perform the task on itself. So we extended that to a deep interactive learning approach. So to be able to directly work from raw high dimensional, in this case, images. What you could say, we do the simplest thing that comes to your mind is say, okay, let's just train some encoder, decoder, autoencoder structure to bring it down to a manageable representation, and then we can use that learned representation to learn a policy. That obviously has the advantage that you can pre-train everything and that you can use lots of data you might get from something else, and it might be a bit quicker, but in the end it turns out, and as you can imagine, is then if you do that, you're stuck with that representation and it might not be the perfect fit for your tasks. So you can also do the same thing online, where we now effectively have two training criteria for our neural network, where we at the same time train the autoencoders, so the reconstruction here. So we train a good representation and the policy. And it turns out that this is actually as fast as doing it in the offline way, and we get better results. So that's work from one of my PhD students, Rodrigo. So that's how it looks like here. That's Rodrigo remote controlling a little mobile robot in Ducky Town. He has a laptop in his hand and occasionally providing corrections, exactly like we saw in the previous slide. So it stays on the right lane. On the top here, you see the true camera image, and on the bottom, that's the reconstruction. And if I skip forward a little bit, you're going to see here that he can then take off his hand, so no longer provide any corrections or no longer remote control the little car, and it learns within a couple of minutes to do this task from scratch. So if we're thinking about driving, one other important aspect is how fast are we actually going? And if you're just doing that based on the images, that's something that's not contained. So for quite a number of tasks, you might want to additionally include some form of memory, either to be able to reconstruct the full state you need, or in some other cases, if you literally need to memorize something that happened in the past. So very similar to what we had before, the major thing that changes is, yes, we have a recurrent neural network now, and rather than decoding directly the image we see, we now decode it to the next time step. So it automatically also learns what it needs to predict the next state based on the current observation and the action we take. So it looks something like this. Again, on the right, the camera input, what the network sees, which is only here, this part in white, and then the reconstruction. So what the robot is trying to do is to touch these fake oranges, but it's a bit tricky because it needs to memorize where they are here in this white part, and then move accordingly a bit later. And already after 5 minutes, it can do the task very well. Again, trained from scratch. And then if you train it a bit longer, in this case, 45 minutes, it's close to perfect. Having already a good representation is actually very handy, because then you can also go ahead and learn a related task. So in this case, we have fake pairs, which you want to avoid. And because it already has a good representation in the network, it can learn that really, as you can see here, in real time within 3 minutes to learn this similar but still slightly different task. So far, what I showed was all about corrections in action space, which has a number of advantages. It's direct, but if you think about a robot like this, it's high dimensional, and it can quite often be very non-intuitive, which joint do I now need to move while I'm actually interested in the position of the end effector. So what you could do instead is say we provide the corrections in state space. The downside of that is that we need some form of an inverse model. So a little video of that. Why is it not playing? So here the task is to track the circle on the whiteboard with the laser pointer. And here we actually also don't have a model of the complete system. Yes, you could get the model of the robot very easily from the manufacturer. But then what we're actually learning is the complete model and how you need to correct and how that maps to actions in state space. And here we're writing the name of our department on the whiteboard as a test. So now let me switch to interactive reinforcement learning. We're going to actually use very similar ideas to what I've been showing you before. And we're going to combine this interactive corrections, which you can see as a form of supervised learning, with reinforcement learning. Combining human demonstrations and reinforcement learning is nothing new. That's over 10 years old now. Some of my early work where we started with an initial demonstration, and then if you just played it back, it misses by a bit. So you need to fine tune it with reinforcement learning. And then it takes some 40 trials or so until it sometimes goes in, but usually bounces off. And after 100 trials or so, it has nicely converged. And I'm going to come back to that example in a couple of minutes. That's why I'm showing it. So the kind of related to that, the first idea you might have on how can we combine interactive learning with reinforcement learning is, again, do this two-step approach. First, use coach, which I introduced a couple of minutes ago, to train it in a supervised fashion, in imitation learning fashion, and then fine-tune it with a policy search. Compared to the video I just showed, the advantage would be that here we're directly training it on the robot, so we don't have this additional step in between where some of the details might get lost and it's not working as well on the real robot. But actually, we wanted to take it a step further and really integrate the two of them. So to get the interactive corrections within the reinforcement learning loop. So here I'm going to talk first about policy search approaches, but I think you can also apply it more generally to other reinforcement learning approaches. That's how a typical rollout reinforcement learning loop looks like, with the states and then taking action, you end up in the next state and get the rewards. And very importantly, you also have the exploration. So the idea we came up with is, how about we actually model the interactions, so the interactive corrections we get from the teacher, what Benji called the human advice, as a form of exploration. So the advantage of that is that it very naturally integrates with the rest of the algorithm. It just treats it as an additional data source. There are a few details there. So in particular, you don't want to combine regular exploration where the robot is trying something out with human guidance, because that's very distracting for the person that is trying to correct something, and then you never know if it's now you not doing something correctly or the robot and its exploration is working against you. So here we effectively have a switch that if the human teacher is guiding the robot, then we switch off the regular exploration. And then for the rest, it's a pretty standard policy search loop. So you do an episode, and then either you have human guidance or exploration, you evaluate the cost of the rollout, and then you use some policy search methods to update the parameters here. So how does that look like? That's again ball in a cup, and is now learning from scratch, but we have additional e-caller sitting in front of the robot and giving it interactive corrections on how it should change the movement. So here, after 11 trials or so, we're already pretty close. And then I think that's around 25 trials or so, it already manages to catch the ball in the cup. So here are some plots to compare that. Again, if in this case, if we go back to the idea of starting with an initial demonstration, here in red, you have policy search, so just reinforcement learning. In green, you have the interactive imitation learning, which I was talking about in the beginning of the talk. And in blue is what I just introduced, the combination of policy search and interactive corrections. So here in the beginning, you see that the interactive approaches are roughly equally fast. However, in the end, really having the robot optimize the movement itself also pays off because we get a slightly lower cost. And policy search without any interaction takes a bit longer, but not drastically so. That picture changes drastically if we now start from scratch. So if we initialize the policy to all 0 effectively in this case, and there until the reinforcement learning has come to some strategy that works takes really an awful lot of time. So 3 times as long or even longer. And which is also very intuitive in the sense that a human teacher has a good understanding of what needs to be done and can give the overall rough strategy very quickly. And then again, here we see that the robot can fine tune it a bit in the end and really make it precise and reproducible to get the best cost possible. That also nicely connects to what Benji was talking about. I like that quote. I'm inconsistent because I'm human. So yes, we need to deal with the fact that the demonstrations or even the corrections we get might not be perfect. So what one of our master students came up with is actually a way of merging various uncertainties related to the policy of what the robot is learning and the human feedback. So what we have here is some kind of an action space, and then here you see a bunch of probability distributions. So in blue, that's the policy a reinforcement learning agent has learned, probably rather at the beginning of the learning process, because it's still very uncertain about what to do. And then we get some human feedback, which probably is also noisy. And if you get multiple instances of feedback, we can also estimate that distribution. And then the idea is, so how do we combine the blue curve and the orange one? And if you think about it, it's kind of like a Kalman filter where you trade off the different sources of information you have, the different models you have, and the associated uncertainties with that. And that's exactly what we're doing there to smartly combine what the reinforcement learning agent already knows and the human feedback we get. And in practice, for estimating the uncertainties, we're using multi-headed neural networks. So the structure roughly looks like that. We have an actor-critic framework. Additionally, we have the human that is providing corrections. And again, if the human is providing corrections, we do some kind of a switch between who is in control. And what we have additionally here is a predictor that is actually learning what a human tends to do in terms of corrections, which allows us to deal with a lot sparser human corrections and also to estimate the uncertainties. So we haven't tried that on a real robot yet, unfortunately. So here are a few examples in simulation on mountain car and pendulum swing up. In red, what you see is DDPG, so pure reinforcement learning, deep reinforcement learning. In blue is the proposed approach. In orange, an ablation without the prediction model. And in green, again, coach, deep coach, which is the imitation learning approach, pure imitation learning. So on the top, that's the returns. And on the bottom is the kind of the amount of feedback you give per episode as a teacher. And again, here you can see that reinforcement learning, pure reinforcement learning takes quite a bit longer. If we have the human in the loop, that goes a lot faster. And the one thing that might be a bit surprising here is that the imitation learning approach is really, really slow here, which is due to the fact that the pendulum is pretty fast. So really providing corrections and correct corrections is tricky. So further look into that, you see a very similar plot here. What we additionally have is the different types of lines, which in this case, a simulated human is the error level. So if a human provides a correction, how often is it actually the correct action, and how often is it just random? And the more randomness you have, the worse the imitation learning approaches perform, and there you can really see a drastic difference in both settings. However, that's a lot better if you combine it with reinforcement learning. So there the agent itself, by being able to judge whether the correction results in a high reward or return in this case or not, can compensate for all these errors you make. And I mean, in the limit, if you have just random actions in terms of advice, then it falls back to what you have as a more standard exploration strategy. Final thing I wanted to show you is an attempt to make inverse reinforcement learning interactive, because the two approaches I showed you so far assume that the goals of the human and the robot are perfectly aligned, that the human advice is actually helping the robot to achieve the task that is defined by the reward function. So here, that's actually the task. The robot is trying to track the red target on the screen with a camera and have it in the center of the frame. And here we're learning at the same time the policy and the reward function using some pretty classical inverse reinforcement learning approach. And here what you see now is, in the end, the validation of the learned reward function and policy by tracking a real red ball. So to sum up, I've shown you a few examples on how you can incorporate human interactive corrections in reinforcement learning and also in imitation learning. We've seen that this speeds up the learning process quite a bit. The examples I've shown you are fun. Oops, why is it advancing automatically? But we're still quite a far away from actually making it useful in even semi-structured environments like a supermarket. And that's something we're currently working on to really scale those approaches up and see how far we can push them. So to sum up, having a human in the loop during the learning process can speed up the learning process quite a bit, and it's hopefully also intuitive for the human teachers. I showed you a few different ideas on interactive reinforcement learning. The first one was how to model the interaction as exploration, and the second work I showed you was on how to also make use of an estimate of the uncertainty associated to the human corrections and the things the robot has already learned. And one of the big questions is, how do you actually make sure that the robot and the human are trying to optimize the same thing and are not fighting against each other? Thank you. So,
thank you very much, Jens, for your presentation. Remember, guys, by the way, that you can ask your questions at any time during the presentation in the chat. We will have a look at the end of the presentation in case you have something that you want to discuss. I have a question, Jens. When you were talking about the interactive correction,
yep.
that what came to my mind, this concept of scaffolding, which is quite used in developmental learning and developmental robotics. So I was wondering if in your experiment you have used similarly in that way. I mean, that removing the help of the corrections, also focus those at the beginning and then removing them over time.
That's an excellent idea, I think. So no, we have not enforce that. It's something that more or less happens automatically, in the sense that in the beginning the robot is still doing strange things, so you as a human teacher are very much inclined to jump in and correct things, and then over time, as the robot starts to perform better and better, the teacher also usually feels less and less need to correct. But yeah, I think that's an excellent idea for a direction to explore on how to make use of that idea on kind of the
scaffolding. Yeah.
the scaffolding. Yeah.
The other thing is, how are you dealing with the with human patient? I mean, well, you have this interactive approach. Of course, the number of interactions are or can be sort of limited sometimes, because of course in experimental setups you can be there for longer, but in real world scenarios that could be an issue. So
yes.
are you measuring the time, the times of interaction, things like that, something like to deal with that?
So yes, we are measuring that, and especially for some of the imitation learning, interactive imitation learning things, actually, which I've not talked about that much. There's some more work we've been doing lately. We also started to do user studies to evaluate how they like to teach and what they prefer. And in general, they seem to like this interactive approach versus just doing plain learning from demonstration. And some of the newer things we have, again, for imitation learning, you can really teach a robot within 2, 3, 5 minutes. So there, but indeed, if we require half an hour of interaction, then the human patience becomes the limiting factor, and they become less concentrated, make more errors, become more random. So yeah, that's tricky. And then I see a question in the chat.
Yes. Thank you very much.
Still have time?
Yeah, we have time for a last question. Yes, we can take this one. It said in slide 25, is there a way to measure advice that could inform the robot of new concepts that they would not otherwise encounter? More like continuously shape their learning to adapt in a new environment.
Let me see, what was slide 25?
I don't have any in my mind either.
Okay, let me just share my screen again.
Sure.
There we go. Yes, excellent question. Yes, that's one of the things that we want to work on how to also make the robot more active, on actually requesting advice on things that would be helpful for it to learn quickly. And sorry again, we've been working on that in the imitation learning setting, and there it works very nicely. And yes, we're going to try that in reinforcement learning as well.
Okay, thank you one more time, Jens, for your presentation.